Hey everybody, Mr. Sternary here, and today we're going to be starting our unit on gases. Particularly, our lesson today is going to be on the kinetic molecular theory and gas properties. And I'm going to say this now, and I'm probably going to say it a couple more times throughout this unit, that you already know a lot of the stuff that we're going to discuss throughout this unit. Intuitively, you know what's going to happen with gases, even if you don't think you do right now. We're just going to add some math in there to reinforce everything that we already know. So when we start to look at all this stuff, just keep in mind that you're going to know more about this than you think, and this is just going to reinforce everything that you already know. Before we get into it, let's define some objectives for today's video. We want to be able to understand the postulates, or kind of the ideas that are going to make up this thing that we call the kinetic molecular theory. I'm going to abbreviate it KMT. We want to then use that KMT and apply it to some real-world examples to kind of connect the science and what we actually observe in real life. And then we want to kind of understand the measurements that we're going to see through the rest of this unit as we start to describe a sample of gas, no matter what sample we're looking at. Before we jump into the KMT and describing all the units and the actual math behind it, let's take this balloon example that I've got up on your screen right now. Any kind of gas that we're going to be describing is going to be described by the same general ideas, whether it's in a balloon, whether it's in a basketball, whether it's in a hot air balloon, or if it's just the gas in the room around you. So we can think about describing this sample of gas in this balloon by how much space it takes up. Is it a small balloon? Is it a large balloon? Is it a nice big hot air balloon that's going to travel, all the way through the fields, wherever it is? Doesn't matter. How much space is this gas actually going to take up? What's the temperature of that gas sample? Is it a hot gas? Is it a cool gas? How does that affect how much space it is going to take up? How much pressure does that gas exert? The only way this balloon stays afloat, or stays inflated, I should say, is by this gas exerting some kind of pressure, by pushing off of the walls, or I should say the inside of that balloon, right? We can figure out how much pressure that's going to exert. And then this example is nice and easy because I can go through and I can count all these little gas particles inside my balloon. I can say 1, 2, 3, 4, 5, 6, 7, and I can keep going throughout all of them. But lots of times we might not be able to count them like that easily. We might have to go through and do some math and do some fancy math, figure out how much space it takes up, what's the temperature of that gas, how much pressure is it exerting, and kind of figure out how much gas we have in that sample. So what I want you to try and do is think about this balloon example throughout the entirety of your unit, not only today, but through the entirety of the unit, because this is going to be kind of key for us. If you can understand how we start to think about a balloon, is it a big balloon, a small balloon, is it hot, is it cold, how much pressure, is it a really tight balloon, or can I kind of squish it around? That's going to be important as we start to move through this particular unit. All right, let's move on to our kinetic molecular theory. This theory is going to describe, when you guys get to physics next year, you're going to hear kinetic, potential energy, kinetic energy, all that kind of stuff. So kinetic, I'm going to give you a kind of sneak peek, is about moving, right? So how do molecules move around compared to each other? That's really our definition for the kinetic molecular theory. And there's going to be 5 or 6 different things that we are going to look at that make up this theory, that are going to describe how particles move around in a sample. The first one for us is that gases are always moving in constant, rapid, random, straight line motion. So they move like pool balls. If I move a gas particle and I set it in that direction, it's just going to keep moving in that direction. It's not going to stop until it hits something, kind of like the pool balls hit the sides of the pool table. All gas particles are going to move in that constant, random, straight line motion. They're not going to kind of go wavy and like a roller coaster. They're just going to move in a straight line every single time until they hit something, and then they're going to get redirected and move somewhere else. There are no attractive forces between gas molecules. All right, that means they're not going to end up attracting to anything. If they bump into each other, they're going to move apart. If they bump into a wall or they bump into the container that they're in, they're not going to get stuck to anything. They're just going to keep moving until they can lose all of their energy. And that kind of moves into the third idea, is that all these collisions between the gas particles are elastic, meaning that they don't stick together. Think of pool balls. When a pool ball hits another one, it just moves it. It doesn't stick together and they don't move together. If a gas particle hits another one, it's just going to move on and bump the other one in another direction. Gas particles occupy negative or negligible volume, meaning, it sounds more complicated than it is. Our gas particles are going to be really, really, really tiny gas particles, and there's going to be a lot of space between them. So when we think about it, the gas particle size is pretty much insignificant when I compare it to how much space it takes up. In other words, there's a lot of empty space between all our gas particles, and that's going to be important when we start to look at this later on. This one you guys should already know that the Kelvin temperature is directly related to the energy. The hotter something is, the more energy it's going to have. We kind of talked about this way back in the beginning of the year when we started looking at all our different scientific units. The Kelvin temperature for us is going to be directly related to our kinetic energy. And the last one is our pressure of a gas is going to be related to the number of collisions against the walls of the container. So if I have a lot of pressure, that means I'm getting a lot of collisions onto the sides of whatever I'm talking about. It could be a tank, it could be a balloon, it could be a water bottle if I've got a gas filled up with the water bottle. Either way, the pressure is going to be generated by those collisions against the wall. How do we see all this in real life? Well, our postulates or our ideas are actually pretty easy. So our gases are tiny molecules in mostly empty space, right? That's evidences in compressibility. If I've got a lot of space in between my gas particles, I can kind of shrink it down and push them together, right? There's going to be now less space in between them, and they're not going to take up as much volume compared to what they were when they were expanded. There's no attractive forces between the molecules, right? That means that they don't clump together. If I sprayed some perfume on this side of the room, the other side of the room would eventually smell it because there's no attractive forces between them. The particles are going to spread out. They're not going to clump together and stay on this side of the room. Molecules are in constant random motion. That also plays into our perfume idea where if I spray the perfume or the cologne, it's going to spread out and it's going to mix. They don't clump together, and they're going to mix and try and fill up the entire room. All right, we've got molecules collide with the walls of the container and another. That just means that we're going to see pressure in our sample. And the last one, our kinetic energy, is proportional to our Kelvin temperature, meaning the hotter the temperature, the more energy they have. Think of car tires in the summer and the winter. In the summer, you have to let the pressure out of the tires just a little bit because now it's warmer outside, so there's more energy in there. The tires are under more pressure. In the wintertime, you tend to overfill your tires. So this way, when the temperature cools down, you have enough gas particles in there to maintain your pressure because as the temperature goes down, their motion goes down, they don't have as much energy. If they don't have as much energy, they don't exert as much pressure. All right, let's very quickly talk about our properties and our characteristics of gases. First characteristics. A lot of this is going to be similar to our kinetic molecular theory. Gases expand to fill any container, and they can be compressed, meaning there's no real volume to our particles. All right, they just take up a lot of space, but the particles themselves don't have volume. All right, there's just a lot of empty space there that can be filled in when I compress that gas sample down. Gases are like liquids. They are what we call fluids. There's no attraction between them. I can push all the gas molecules if I wanted to one side of a room. I can compress them down. I can move them however I want them. All right, just like I can take a liquid and I can pour it into any container, any shaped container, any size container I want. All right, gases can do the same thing. They are fluids. And gases have very low densities. All right, that kind of goes back to our idea of the particles don't take up volume. They just have a lot of empty space between each particle. All right, I've got some pictures down here to help you understand what we're talking about. If I look here, a solid, a liquid, and a gas, there's not much space in between all these particles in our solid and our liquid. But once we create a gas, look at how much space I've got now in between all my molecules. And when we start thinking about that, I can move them however I want, like fluids. Right? I can take them, if I look over here on this example, I can take them and I can compress them down. Because there's so much space in between them, now when I compress it, now I'm offering it less space, and they're just going to move and they're going to fill whatever space I give them accordingly, just like a liquid. All right, so when we start thinking about the properties of a gas, we can use a lot of the math to start to model the different properties and the characteristics and the behaviors of our gases. It's going to depend on 4 different variables that we're going to explore throughout the next couple lessons. The first one is volume. All right, and I measure the volume in liters, that's a capital L, and the variable that I'm going to use to represent that is a capital V. The next one is temperature. We could measure it in Fahrenheit, we could measure it in Celsius, but 95% of the time what we're going to do is we're going to measure it in a unit called Kelvin that we've already talked about. You guys should know the conversion for it. We talked about it way back in the beginning of the year. The third variable is going to be pressure. And the unit that we're going to use, we're going to talk about a couple more coming up, but the unit that we're going to think about that's going to be associated with pressure is what we call atmospheres. And you're going to see it abbreviated ATM. And the last variable that we're going to use when we start to model our gases is going to be the amount of a gas. Think back to the balloon when I was counting all those purple little gas molecules. That one was a really easy example. But that was just to show how I could go through and count them. Lots of times gas molecules are very, very small. So what we have to go through and do is use a unit that we call the mole to help us count the amount of the gas that we have. That one's not going to be as intuitive. If you notice, volume is represented by V, temperature is T, pressure is P, and for the amount of a gas, we end up using the letter N to represent its variable. You're also going to start to see something called standard temperature and pressure. You can have a reference point, right? Because it can be really hot, it can be really cold, there can be a lot of pressure, there can be a little pressure, but we have to have a reference point that we can start to compare our sample to something else. And that's what standard temperature and pressure is going to be for us. And there are going to be values for that. And what we're going to go from here on out, when you hear standard temperature or standard pressure, you're going to be thinking of these things. So our temperature, standard temperature, is 273 Kelvin. All right, that's that standard. When I think of temperature and I think of standard temperature, I'm going to think of 273 Kelvin. For my pressure, we have 1 atmosphere, and then we're going to have a couple more units. We're going to have 760 torr, we're going to have 101.3 kilopascals. We'll talk about this a little bit more in class, but the ones that I want you to remember, temperature, standard temperature is 273. Standard pressure is going to be 1 atmosphere. You might also see it abbreviated as STP for standard temperature and pressure. Let's just recap very quickly. Our gases are going to behave based on the ideas or the postulates of the kinetic molecular theory. Those 5 things that we talked about before, 5 or 6 things I should say that we talked about before. Our standard temperature and our pressure. The standard temperature is 273 Kelvin. Our standard pressure is going to be 1 atmosphere. We're also going to have some equivalents for that. If I have 1 atmosphere, it means I have 760 torr. If I have 1 atmosphere, it also means that I have 101.3 kilopascals. Thanks for watching. Hope you guys enjoyed the video, and I'll see everybody in class.